Okay, this is continuing where we left off on chi-square. So here I mentioned you could kind of get a bit of a feel for um, whether you'd get a big chi-square or a small one, just based on how much these differ from the expected counts. And you can see there's not a whole lot of difference, and you can also start to see, yeah, this drug probably didn't help much because you actually had smaller than expected here and bigger than expected successes in the placebo. And same, you had more than expected relapses for the drug and smaller than expected for the placebo. So, it looks like you're probably not going to see a significant effect of the drug. Now, there could be that the placebo actually helps more than the drug, or it could just be due to chance, which is probably more likely. And so when you actually crunch it out, you can see that the chi-square is 0.315, and the p-value associated with that is actually like 0.57. So you would not reject the null hypothesis in this case, that the drug and placebo, or the treatment is related to outcome. Okay? Or, yeah, that the treatment is not related to outcome. You would not reject that null hypothesis. Okay, so as I mentioned, you're not going to run these calculations, but I want you to kind of get a feel for what it would look like if you had a significant versus a non-significant chi-square, large versus small. So let's say you have a die, and you're rolling it, and you want to know, is this a fair die or a loaded die? Okay, so if it's loaded, then one or more numbers are going to be more likely, and if it's a fair die, then all of them will be equally likely. Okay, so let's say you roll it, I think I have it 60 times here, and these are the observed counts, okay, for 1s, 2s, 3s, 4s, 5s, and 6s. 10, 11, 9, 10, 11, 10, okay? Now, these look to be pretty even, so even just kind of looking at this, if you think through here I've added a little bit more information. Oh, actually, I made it, I reduced it by 1 here just to make it even 60. If you roll it 60 times, the expected counts would be just 60 divided by 6, so 10 for each number. Okay, and you can see that all of these observed counts are all about even, and they're all pretty similar to the expected counts. So this is the scenario where you would probably expect, and of course, you're always going to want to actually run the test, but just to get a feel for whether this would pass the stink test or not, you would probably expect a small chi-square, and this is probably a fair die. These all seem to be pretty close to the expected counts and all pretty even. Okay. However, if you were looking at this kind of scenario where you roll it a bunch of times, and instead you're saying, 1, 5, 3, and then 6, you roll that 23 times. This is going to be a larger chi-square, okay? Remember, you're going to take the expected count. I don't know if this actually adds up to 20 or up to 60, but it's going to be, some same number across all of these, and it's going to, this is going to differ from that substantially. And so this is going to be a big difference, and it's going to add to the size of the chi-square. So you probably get a large chi-square here, probably get a low p-value, and you probably reject the null hypothesis that all of these are the same, that it's independent of which number, and it's probably not a fair die. Okay, going back to our original example, I actually calculated the chi-square for this one, and I made it nice so you got like the same row totals. Remember, to get these expected counts, it's the row total times the column total divided by the grand total, the total. So here we got 485 through 3365, 3365. And you can see that there are some pretty substantial differences, 550 versus 485. And also the difference is swapped. The pattern is swapped depending on if you're Republican or Democrat. So chances are something is going on here. And sure enough, if you actually crunch this out, you get a pretty big chi-square and a very low p-value. Okay, so that's about the size of what I'm hoping that you'll understand. Is just what we mean by observed and expected. And if you're seeing big differences between observed and expected, then you would see a larger chi-square. If you're seeing smaller ones, then it's a smaller chi-square. Bigger chi-square, lower p-value, smaller chi-square, larger p-value, and so you usually would, if it's over 0.05, then you would not reject the null hypothesis. Okay, that's all.